Let me tell you something quietly strange tonight. As you lie back and let your breathing slow down, I want you to imagine that every particle in your body has a shadow twin. Not a ghost, not a spirit, but a kind of mirror version made of antimatter, matching you in almost every way. Think about that for a moment. Every electron in your fingertips, every proton in your bones, every tiny piece of you paired with an opposite that carries the same mass, the same basic presence in the world, but opposite charge. A cosmic reflection you never see, and yet, according to our best mathematics, is written into the same rules that made you. Here's the unsettling part. If matter and antimatter were truly perfect mirrors, if for every one of your particles the universe had made an equal and opposite twin, then a very long time ago everything should have met its reflection and vanished. The newborn universe should have destroyed itself in a flash of light, leaving behind no stars, no planets, no quiet rooms, no you lying here listening in the dark. And yet here you are, breathing, existing, feeling the weight of the day slowly drift away in a universe that somehow chose matter over antimatter, as if the mirror cracked just enough to let reality slip through. That's where CERN comes in. Deep underground, beneath fields and cities, someone has built great rings of metal and vacuum, machines that take tiny particles and push them almost to the speed of light, trying to recreate in miniature the first moments after the Big Bang. It sounds loud and dramatic, but the real work is surprisingly quiet. People watching screens, comparing numbers, looking for the smallest differences between matter and its antimatter twin. Lately, those experiments have started to whisper something new. By trapping atoms of antihydrogen, by letting them fall, by listening to the faint light they give off, CERN is finding hints that our old picture of a perfect cosmic mirror is bending. Not shattering into nonsense, but flexing, revealing fine cracks in ideas we once thought were absolute. In this video, we're going to walk through that story slowly. From the first time antimatter appeared as a line in an equation on paper to the moment someone saw its trace in cosmic rays from space. From the ingenuity it took to bottle antihydrogen in magnetic cages to the newest measurements that tell us, with almost absurd precision, how this shadow version of matter behaves. Some of it is going to be detailed and some of it will feel almost dreamlike, and all of it will unfold at a pace you can drift with. You don't need to keep up with every technical step. You can just lie there, let the ideas wash over you, and follow the gentle question underneath it all. What does it really mean that reality has a mirror and that the mirror is not quite the same? So let me tell you where that question quietly begins. Right now, wherever you are, you're surrounded by something so familiar that you almost never think about it. The pillow under your head, the phone on your bedside table, the walls of the room, the bones in your hand if you lift it up in the dim light. All of that is matter, solid, ordinary, slightly boring matter. If you could zoom in past the fabric threads and the glass and the paint, you would find the same little building blocks repeating. Tiny particles called electrons, and deeper inside the atoms, protons and neutrons, arranged in patterns that stay put for a very long time. The pillow does not suddenly explode, the wall does not melt into light. Everything just sits there, quietly, obeying rules it has followed since the beginning. Think about a single atom in that wall, maybe a hydrogen atom drifting in, a bit of moisture. One proton in the middle, one electron buzzing around it, held together by electric attraction. It is so simple, it is almost funny. 1 + 1 in the language of particles. Now imagine that every one of those particles has a twin. Same mass, same tendency to exist in the same places, but with its electric charge flipped like a photograph printed in negative. The electron's twin is called a positron, the proton's twin is called an antiproton. Neutrons have antineutrons. For every piece of matter there is an antimatter partner, as if the world came with a built-in mirror. Here's what we do know. If you could build a hydrogen atom out of those ghostly twins, you would get anti-hydrogen, an antiproton in the middle, a positron around it. If you looked only at its mass or at the colors of light it can absorb and emit, most experiments would say, yes, this is just hydrogen again. The same energy levels, the same spectral lines, the same quiet structure. But bring the two together, hydrogen and antihydrogen, and the story changes. When matter and antimatter meet, they do not bounce or smear or politely pass through each other. They annihilate. Their mass is converted into pure light, a burst of energy rushing away as high-energy photons. Two atoms gone, leaving only ripples in the electromagnetic field. There was a time, a very long time ago, when the whole universe was dense enough, hot enough, that matter and antimatter were being created and destroyed in this way all the time. If there had been exactly the same amount of each, everything should have cancelled, and the cosmos today would be nothing but light expanding into darkness. And yet you have a pillow, you have a phone, you have a world made almost entirely of matter. That's where CERN enters our story. In long, quiet tunnels under the ground, people have learned to make tiny drops of antihydrogen, to hold them in magnetic traps and to compare them with ordinary hydrogen with exquisite care. They watch how they respond to electric and magnetic fields, how they fall in Earth's gravity, how the colors of light they absorb line up. We honestly don't know for certain whether there's some tiny mismatch hiding there, or whether the mirror really is perfect. Those almost invisible differences, or the stubborn lack of them, are what the new results are about. And all of it will lead us deeper into the question of why anything, including you, is here at all. So let me tell you what those almost invisible differences would actually mean. To see it, you have to go back to a very long time ago, to the first instant after the Big Bang, when the universe was not stars and galaxies, but a kind of blinding fog. Not empty space with a few sparks in it, but a thick, glowing soup where there was no clear here or there, no up or down, just energy boiling everywhere at once. In that fog, particles were not rare, precious things. They were constantly popping into existence, always in pairs. One particle, one antiparticle, two tiny partners, like a couple stepping together onto a dance floor made of light. Think about that picture for a moment, for every electron and anti-electron. For every proton and antiproton, each one carrying the same mass, the same amount of charge, just with the sign reversed, like matching socks turned inside out. Here's what we do know. The equations we trust most, the ones that successfully predict the behavior of your phone and of distant quasars, say that the Big Bang should have created almost equal amounts of matter and antimatter. Not exactly perhaps, but so close that in that first fraction of a second the universe was essentially a perfect ballroom of these dancing couples. As the universe expanded, it cooled, the fog thinned, the dancers slowed. And when a particle met its antiparticle, they didn't bounce or argue or politely pass by. They annihilated. Their mass turned into pure radiation, a flash of energy racing away at light speed. It's so simple, it's almost funny. You touch your opposite and both of you vanish. If everything had gone exactly by the book, almost every couple would have met again. Almost every particle would have found its antiparticle partner in that early crowd. The universe would have cleaned itself up, leaving behind a smooth bath of light and almost nothing solid. No stars burning quietly in the dark. No planets cooling slowly. No sleeping humans listening to someone talk about antimatter on a screen. And yet, that is not the world you wake up in. When physicists look at the numbers, they find something astonishing. For roughly every 10 billion matter-antimatter pairs in that early fog, there seems to have been one extra matter particle with no partner. Just one unpaired survivor for every 10 billion perfect couples. Those lonely leftovers are what everything you see is made of. Every galaxy, every atom in your body, every neuron that holds your memories is built from that tiny excess, more remarkable than fire, more remarkable than language even. But why was there any excess at all? Why did matter win by just that hair's breadth instead of vanishing into light with everything else? We honestly don't know for certain. That's where CERN quietly becomes a kind of forensic lab for the universe's earliest crime scene. Because if there is a hidden rule that tipped the scales in favor of matter, some of it is going to be written into how antimatter behaves right now. And all of it leads to a very unsettling possibility that in those underground rings and traps, scientists may already have seen the first hints of how reality cheated the perfect mirror, and they are not sure yet what exactly did the cheating. So let me tell you where we go from that unsettling possibility. There's a temptation when you hear words like CERN and antimatter and broken reality to brace yourself for a sprint. A rapid-fire tour, one strange claim after another. This is not that. We are going to walk through this slowly. You do not have to hold every name, every date, every equation in your head. You can drift a little, let your attention soften, and the story will still be here, unfolding at a gentle pace, like following a single line of ink across a very long page. Think about this as a thin, bright thread running through time. At one end, a very long time ago in the late 1920s, there's someone standing at a chalkboard, Paul Dirac, trying to write down an equation for the electron that respects both quantum mechanics and Einstein's relativity. On that board, in symbols and square roots and minus signs, something impossible appears, solutions that look like electrons, but with the opposite charge. On paper, they should not exist. And yet the mathematics is stubborn. The negative energy pieces refuse to go away. That is where the idea of antimatter is born, not in a laboratory, but in the quiet realization that the numbers are telling you about a second world, a mirror world, interwoven with this one. From there we follow the thread up into the sky. A few years later, balloon experiments ride high into the atmosphere, instruments waiting for cosmic rays. In those showers of particles from space, someone finally sees the first positrons, the anti-electrons that Dirac's equation whispered about, little bright flecks on photographic plates, proving that the mirror is not just an idea. Then the journey comes back down to Earth and forward in time into machines. Physicists learn not just to notice antimatter, but to make it, to bend it with electromagnetic fields, to cool it, to trap it. At CERN, rings of magnets shepherd protons to nearly the speed of light, letting their collisions briefly call whole families of antiparticles into being. The thread narrows again from vast tunnels to tiny clouds. In experiments like alpha and A-trap, whole atoms of antihydrogen are assembled and held in magnetic bottles hanging there, effectively weightless, while lasers probe their inner structure. Other teams, like Alpha G and G-bar, simply watch to see how these ghostly atoms fall, asking whether antimatter feels gravity in exactly the same way you do. Along the way, we will keep circling back to a few quiet themes: symmetry, and the ways it can break the strange near equality of matter and antimatter, and the equally strange fact that the universe chose one side. The question of why anything exists at all, which sounds so simple. It is almost funny, and yet it is the deepest gap in our understanding. Here's what we do know: by the end of this walk, you will have a different picture of reality. Not as a solid, obvious thing, but as a delicate balance of almost perfect mirrors. And CERN's newest measurements in those underground rings and fragile traps are beginning to show us where the mirrors start to warp, and what that might mean for the world you wake up in tomorrow. To understand why those mirrors matter, you have to go back to something very simple: symmetry. Think about a butterfly's wings, left and right, repeating the same pattern of color and curve. Think about a human face, almost the same on both sides, so that a tiny difference becomes strangely powerful. Think about a snowflake, turning it in your hand and seeing the same star over and over again. That quiet repetition is what your eyes call beauty. Physicists, let me tell you, feel something similar when they look at an equation and see it stay the same after a change. For them, symbols on a page can have the same calm balance as a snowflake under a microscope. If you flip a sign from plus to minus and the rule still works, that is a kind of hidden symmetry. If you reverse the direction of time in the symbols and the pattern survives, that is another hidden balance, a secret echo in the mathematics. In the early 20th century, while the world was learning new words like relativity and quantum, someone writing down these new laws kept running into that echo. Positive and negative charges, left and right, spins, matter behaving one way, and the equations quietly suggesting something else. Something that was not there in any laboratory yet, but was there in the algebra. Here's what we do know. When an equation behaves like a mirror, it is rarely an accident. If you can flip a particle's charge in the symbols and the story still makes sense, that hidden symmetry is usually telling you that some real object is missing from your picture. The mathematics is not just a game, it is a kind of map, and all of it points to pieces of the world you have not seen yet. At that time, people were learning to trust this invisible guidance. Very long time ago, symmetry was just something you noticed in shells and leaves. Now it was becoming a tool. You could demand that a law of nature respect a certain balance, and out would fall new particles, new forces, new possibilities. The hidden symmetry in the symbols was turning into a guidebook for reality. And that's where one quiet, almost stubborn idea appears. If you want an equation that respects both the strange rules of quantum mechanics and the strict speed limit of Einstein's relativity, you cannot simply write anything you like. You must write something that keeps a very precise mirror. When Paul Dirac finally did this for the electron, the result was so simple, it is almost funny. His equation worked beautifully, but it came with extra solutions, like reflections that refused to go away. They looked like electrons, but with the charge flipped, moving through the mathematics as if they were mirror twins. The hidden symmetry had spoken. Long before anyone trapped antimatter in a ring at CERN, the numbers were already whispering, for every electron you know there must be another you have not met yet. So now you have this strange picture in the back of your mind. For every familiar electron, a hidden twin in the mathematics, carrying the opposite charge, waiting in the wings. Let me tell you about the person who had to look that picture in the eye. In the late 1920s in Cambridge, there was a quiet, almost painfully shy physicist named Paul Dirac. He did not talk much. He would sit alone for long stretches of time, walking slowly along the river, or staring at a blackboard, turning ideas over in his head the way someone else might turn a pebble in their hand. Dirac wanted something very specific. He wanted an equation for the electron that did two jobs at once. It had to respect the new quantum rules that told you how particles behave on very small scales. And at the same time, it had to respect Einstein's demand that nothing in the world outrun light. Two powerful pieces of 20th century mathematics, and he wanted to weave them into a single line of symbols. When he finally wrote it down in 1928, his equation was beautiful in a severe, economical way. It was also demanding, because when he solved it, he did not just get the expected answers, the ones with positive energy that matched an ordinary electron. He also got a second family of solutions, with energies that were negative, like reflections below a mathematical zero line. Think about what that means. Energy in ordinary experience is always something you add. You eat food, you gain energy, you burn fuel, you release energy. The idea of a particle with endlessly negative energy sounded like a disaster. If it were real, every electron in the universe would tumble down into those lower and lower states, shedding light without limit. The world would not look anything like the one you see. Most people faced with this would simply have thrown the equation away or quietly declared those extra solutions unphysical and moved on. Dirac did not. The math wouldn't let go. The negative energy pieces were not a small mistake you could erase. They were woven into the structure of the equation, as essential as the positive ones. So he tried a different idea. What if those negative energy states were not holes in the theory at all, but a kind of hidden sea already filled? And what if, when you knocked one of them out, what you saw was not a missing electron, but a new particle entirely identical to an electron in mass, but carrying the opposite charge? A mirror twin. Here's what we do know. That leap, made reluctantly, gave physics the positron, the first piece of antimatter. In Dirac's hands, it was still only an equation, a pattern in symbols. At this point, antimatter existed only as a ghost demanded by mathematics, haunting the blackboard. The question hanging in the air was simple and almost funny in its simplicity. How long would it take for nature to show whether the ghost was real? And when it finally did, what else would come through with it? So imagine this, right now as you lie there listening. The answer to Dirac's ghost is quietly raining through your ceiling. High-energy particles from space, born in distant stars and violent galaxies, are streaming through the atmosphere all the time. They are called cosmic rays. Most of them are harmless. They pass through the walls, through the air, through you, leaving nothing you can feel. But every now and then, one of them collides with the thin shell of air above the Earth and explodes into a shower of smaller particles, like invisible sparks from a grinding wheel. Think about that for a moment. You share your room with a slow drizzle of the universe's debris. No sound, no light. Just tiny messengers from a very long time ago, and from very far away, tracing silent lines through the world. In 1932, someone decided to try to see those lines. His name was Carl Anderson, and his tool was almost comically simple. Not a giant accelerator, just a small chamber filled with alcohol vapor, cooled until it was right on the edge of turning into droplets. It was called a cloud chamber. When a charged particle passed through that mist, it nudged the vapor into tiny beads, leaving a thin white track behind, a scratch in a cloud. Anderson placed this chamber in a magnetic field so that each charged particle would curve as it flew, the way a leaf curves when it floats along a slow turning stream. The direction of the curve told you the sign of the charge. The tightness of the curve told you the energy, and with some care the mass. Electrons were familiar by then. Light, negative, leaving graceful arcs in one direction. Protons were heavier, lumbering curves in the other. Day after day, Anderson watched and photographed these faint signatures, building up an archive of ghostly handwriting. And then one day there was a track that should not have been there. It had the same delicate bend as an electron, meaning the same tiny mass. But it curved the wrong way. In the magnetic field it turned as if it were an electron seen in a mirror carrying positive charge instead of negative. Here's what we do know. That single curve was the first observed positron, the antiparticle that Dirac's mathematics had demanded. In that instant, a negative energy solution on a page became a bright streak in a photograph. A ghost from equations stepped into the world and left footprints in a cloud. So simple, it is almost funny, just a curve on a glass plate. And yet it said antimatter is real. Let me tell you why that matters to you. Every PET scan in a hospital, every time someone's brain activity is imaged or a tumor is mapped, uses positrons. A small amount of a radioactive substance emits them inside the body. Each positron finds an electron. They annihilate, and the resulting light is detected and turned into an image. The machine in the quiet hospital room, the cosmic ray in the upper atmosphere, and Anderson's cloud chamber are all part of the same story. And all of it traces back to that first faint curve, to the moment the universe admitted that it keeps a second copy of its particles tucked away waiting for us to notice. But if every particle has a twin, there's a new puzzle waiting. Why does almost everything you see seem to be made of only one side of the pair? So if every particle has a twin, and the universe likes symmetry so much, you might expect something very simple. A mirror. Not a little mirror on a lab bench, but a cosmic one. On one side, the world, stars burning hydrogen, planets cooling slowly, someone watching this video late at night. On the other side, an anti-world, anti-stars, anti-planets, perhaps even anti-people, all made from antimatter, all following the same mathematics of motion and light, just with every electric charge quietly flipped. Think about an anti-sun rising over an anti-earth, anti-electrons, which we call positrons, swirling around anti-protons to make anti-hydrogen, anti-atoms building anti-rock, anti-water, anti-clouds. From the inside, the experience there could feel completely ordinary. You would drop an anti-stone, it would fall, you would look up, you would see constellations. Nothing would announce that you were living on the other side of the cosmic ledger. And here's the slightly unsettling part. In principle, physics does allow huge regions of antimatter like that. If a whole cluster of galaxies had formed from antimatter a very long time ago, and if it stayed far away from our matter, then from this distance those anti-galaxies would shine, spin and collide, almost exactly like the ones in our telescopes. Cold gas would still fall into dark halos. Stars would still live and die. On a photograph, the numbers would line up. The only obvious giveaway would be at the boundaries, where matter and antimatter touch. When an electron meets a positron, they vanish into pure light, usually high-energy gamma rays. So astronomers have gone looking for those bright scars in the sky, places where a matter galaxy and an antimatter galaxy might be brushing against each other and quietly annihilating at the edges. Here's what we do know. Across the vast scales we can survey, we don't see those scars. We see gamma rays from black holes and exploding stars, yes, but not the steady telltale glow you would expect from whole clusters of anti-stars rubbing shoulders with ordinary ones. If an anti-universe is out there, it is not sharing a border with ours in any simple way. And yet, down in the equations, the symmetry is still there. The mathematics that led Dirac to predict antimatter in the first place treats matter and antimatter with an almost eerie fairness. For every process that can happen with particles, there's a mirror process with antiparticles. On paper, the balance is perfect. In the sky, the balance is broken. That is the heart of the puzzle. The observable universe is almost entirely matter. Antimatter shows up only in tiny flashes, in cosmic rays hitting the upper atmosphere, or in carefully trapped clouds of antihydrogen at places like CERN. We honestly don't know for certain why one side won. Some of it is going to be hidden in details of how the early universe cooled and how delicate symmetries were nudged out of alignment. And that's where CERN's experiments become more than just technical achievements. They are, in a quiet way, attempts to hold up a perfect antimatter mirror and look for the smallest crack. If the universe is not a simple mirror, where exactly did the symmetry break? And what happens if in the next measurement that mirror finally blinks? So before we chase that blinking mirror any further, let me tell you a quieter story. Think about a simple heavy scale. 2 metal plates, a bar across the top, a little needle in the middle. On one side you place a weight, on the other side you place an identical weight. The plates settle. The needle rests exactly at the center. Nothing moves. Nothing is preferred. That stillness is what physicists mean by symmetry. In our world, a symmetry is not just visual prettiness. It is the idea that if you change your point of view in some very specific way, the rules do not notice. Slide everything a few centimeters to the left, and the same experiment unfolds in the same way. Run the same process tomorrow instead of today, and the outcome is unchanged. Turn the whole scene around so that left and right are swapped, and the equations quietly agree. And all of it, rather wonderfully, comes with a reward. When a symmetry holds, something is conserved. If the laws do not care where you are in space, momentum is preserved. If they do not care when you run the experiment, energy is preserved. It is so simple. It is almost funny, a kind of cosmic, if you do not mind, I will keep this, built into the mathematics of the universe. But a perfectly balanced scale is not the only picture you can hold in your mind. Imagine a pencil, balanced exactly on its tip. In principle, every direction around that tip is the same. The air is the same, the table is the same. The laws of physics do not point and say, fall that way instead. For a brief, impossible moment, the situation has full symmetry. Then the pencil falls. It chooses a direction to the left or to the right or toward you. After that, the symmetry is gone, even though the underlying rules never change. The fall did not rewrite the laws. It simply picked one of the many allowed futures and made it real. That quiet choice, that breaking of a perfect balance, is at the heart of the matter-antimatter story. A very long time ago, in the first fractions of a second after the Big Bang, our best ideas say the universe should have been almost perfectly symmetric between matter and antimatter. For every electron, an anti-electron; for every proton, an antiproton. 2 plates of a scale, filled to the brim. Yet when the great annihilation was over, a tiny excess of matter remained. Here's what we do know. Every galaxy, every star, every person listening to this is built from that slight imbalance. We honestly don't know for certain what nudged the cosmic pencil. That's where CERN's new antimatter experiments enter, in their very patient way. They are like someone leaning very close to the wobbling pencil and the table beneath it, searching for the smallest scratch, the faintest breeze, any hint of an imperfection that could explain why it fell the way it did. Keep that pencil in mind. We are going to come back to it. And to the question of what exactly pushed our universe off balance. That tiny wobble of the pencil, that almost invisible push, has a physical address. It lives beneath fields and suburbs on the edge of Geneva. If you could float above the border between Switzerland and France and peel the ground back like the cover of a book, you would see it. Quiet office buildings and glass front cafeterias on the surface. And then deep below, a vast circle of tunnels, almost 27 kilometers around, tracing a loop through 2 countries without anyone in the nearby villages really noticing. This is CERN on the map. It looks like a research campus. In reality, it is a machine to rewind the universe. Not all the way back, but just enough to bring a few drops of the beginning into the present. Let me tell you what that actually means. Inside those tunnels, ordinary particles, usually protons, are taken from a bottle of hydrogen gas and given more and more energy. They are passed from one ring to another, like someone pushing a child on a swing, each push timed perfectly, slowly at first, then faster, until they are moving at just under the speed of light. When 2 of these beams meet, they do not gently bump. They collide with such intensity that, for a moment, the energy density inside that tiny point is closer to the early universe than to the calm air in your room. It is hot without heat, bright without light you can see. And in that instant, energy turns into things. Showers of particles and antiparticles burst out. Electrons and positrons, protons and antiprotons. The raw ingredients for building atoms and anti-atoms, including the anti-hydrogen that CERN's experiments now trap and study. Something that did not exist as an object in anyone's laboratory a very long time ago is now held in magnetic bottles, weighed and watched. To do this, you need more than equations on a whiteboard. You need a place, long, dimly lit tunnels where thick cables run along the walls like roots, superconducting magnets, blue and silver, stretching into the distance, guiding invisible beams. And every so often a cavern opens up around a detector the size of a house, layered with sensors. They are like enormous, silent cameras, waiting patiently for the briefest flash of new physics. On the surface, someone might be drinking coffee under a tree, the Alps pale on the horizon. Underground, a proton beam is circulating, making tens of thousands of laps every second. While you lie still in the dark, these machines keep going hour after hour, repeating the same simple idea. Smash things together. See what appears. Here's what we do know. By recreating tiny pieces of the beginning. CERN turns that old question. What is the universe made of, and why this universe rather than some other, into something we can measure? Some of it is going to be familiar, and some of it, especially when we look closely at antimatter, refuses to behave quite the way our tidy pictures suggest. That's where the latest experiments come in, and where the mirror of reality begins to crack in very precise, very unsettling ways. To see how that mirror cracks, you first have to see how we build the reflection in the first place. Not in the early universe, but here, now in long tunnels under the countryside, where someone is patiently assembling atoms that should not exist for more than a heartbeat. Let me tell you how you make an antiproton. You take ordinary protons, accelerate them until each one carries more energy than a speeding train, and you fire them into a block of dense metal. In that instant, the neat picture of a proton as a single thing dissolves into a shower of other things, a spray of particles and antiparticles boiling out of the impact. Most of it flies away and is lost. But some of it are antiprotons, tiny negative copies of the proton, and with carefully shaped magnetic fields you bend their paths, slow them down and guide them into waiting traps. Even that word trap is a little misleading. What you really have are invisible cages made of electric and magnetic fields, tuned in time like a piece of music, so that an antiproton that arrives screaming with energy is persuaded step by step to become almost still. Not stopped, exactly, just cold, colder than the dark between galaxies. Now you need the other half of the atom. The antimatter twin of the electron is called the positron, and you can obtain it from a tiny radioactive source or from other accelerator setups where light and matter collide and briefly spit out electron-positron pairs. Again, you do the same slow work. You cool the positrons, you collect them, you hold them in their own electromagnetic bottles until you have not just one, but clouds of them waiting. It is so simple in outline. It is almost funny. You just need protons and a metal target, a source of positrons, and a lot of patience. Then comes the assembly. You bring the cold antiprotons and the cold positrons into the same carefully controlled space, not touching any walls, not bumping into stray gas molecules, just drifting through arranged fields. Every so often a positron finds an antiproton and the two lock together. That pair is antihydrogen, the antimatter twin of the simplest atom in the universe. One antiproton for a nucleus, one positron in orbit. But antihydrogen is neutral. It does not feel electric fields the way its separate parts did. That is where magnetic bottles come in. If you design the magnetic field so that its strength is lowest in the center and higher near the edges, then atoms whose internal magnets point the right way will be gently pushed back toward the middle. They hover there, in a small region of space, never quite reaching the walls where annihilation waits. Think about what that means. You have a cloud of antihydrogen, colder than outer space, suspended in an invisible cage of magnetism. Each atom is a question about whether reality is truly symmetric. Here's what we do know. Those atoms can sit there for minutes, long enough for lasers and microwaves and gravity itself to ask them what kind of world they believe in. And the answers they give are where the story turns. Because when you listen closely enough to trapped antimatter, some of it is going to sound very familiar. And some of it is not. So when you ask trapped antimatter what kind of world it believes in, one of the gentlest questions you can pose is simply this: what color are you? Not the color you'd see with your eyes if you could somehow hold a piece of it in your hand. The color it sings with when it's excited. The pattern of light it gives off, line by line, like a quiet barcode written in the language of the atom itself. Every atom has one of these patterns. You heat it or zap it or shine the right light on it, and its electrons jump to higher energy levels, then fall back down, releasing light at very specific colors. Not every color, just a few sharply chosen ones. 3 red lines, a purple line, a faint blue-green. But the idea of that pattern, the pure concept of an atomic fingerprint, is something you only really see when you spread the light out and measure it. That's where spectroscopy comes in. It's just the careful act of taking that glow and turning it into numbers. Hydrogen, the simplest atom, has been the great training ground for this. For more than a century, people have measured its spectral lines again and again, polishing the measurements, checking the theory, coming back with better instruments. The famous 21-centimeter line in radio astronomy, the delicate jumps between energy levels in the ultraviolet, all of it has become a kind of reference scale for the universe. At this point we know hydrogen's fingerprint to absurd precision. So precise that changing the numbers in the theory by a tiny amount would throw off everything from atomic clocks to models of distant stars. Here's what we do know. Hydrogen has told us over and over that the mathematics describing it is astonishingly accurate. Now imagine antihydrogen. Same mass, same charges in magnitude, but with the roles reversed, an antiproton in the middle, a positron circling around it. If matter and antimatter really obey the same deep symmetries, then its spectrum should be indistinguishable from hydrogen's. The same lines, the same spacing, matching, not just in a general way, but down to many, many decimal places. So at CERN, the alpha collaboration does something that, on paper, is so simple, it's almost funny. They trap a cloud of antihydrogen atoms in a magnetic bottle, cool them, and shine exquisitely tuned lasers at them. Then they wait in the dark for the faint whispers of light that say an atom has jumped from one energy level to another. It's like listening for a familiar tune played on a mirrored instrument. Every note by heart from hydrogen. You're waiting to see whether the antimatter version is perfectly in tune or whether there's the slightest telling wobble. And when they listen, the agreement is almost eerie. Line for line, note for note, antihydrogen sings the same song, which only makes the next question more unsettling. Because if the fingerprints match this, well, why does the world we wake up in contain almost no antimatter at all? So let me tell you what almost eerie really means when physicists say it. In one of CERN's quietest experiments, the alpha collaboration takes a single anti-atom of hydrogen, cools it until it is barely moving, and then shines laser light on it to see which notes it will absorb. Not just any notes, but one of the most famous in all of physics, the jump from the 1s state to the 2s state, the lowest rung to the next one up in the quantum ladder. Think about how delicate that is. In ordinary hydrogen, we have measured this 1s-2s transition so precisely that its frequency is known to about 1 part in a trillion. That is like measuring the distance from the Earth to the Sun and noticing if it changed by the width of a human hair. Author set out to ask whether antihydrogen hums at exactly the same pitch. Here's what we do know. Within that astonishing uncertainty, antihydrogen hits the same note, line for line. Its spectral fingerprint lies right on top of hydrogen's. If there's any mismatch at all in that 1s-2s jump, it has to be smaller than what even this experiment can currently hear on paper. That might sound almost boring. Two things predicted to be the same are the same. But in the deep architecture of physics, this is a very sharp test of an idea called CPT symmetry. For charge, P for parity, which means flipping left and right in space, and T for time reversal, running the film of the universe backwards. The principle says that if you flip all three at once, the laws of physics should not notice. Hydrogen and antihydrogen are, in a sense, a CPT mirror pair. If CPT were badly broken, the energy levels inside those atoms would quietly shift. The rungs of the quantum ladder would be spaced a little differently. And that difference would show up as a tiny offset in the frequencies their electrons and positrons can occupy. Alpha's matching spectra say if there's a crack in that mirror, it is very, very small. So small that this transition, measured with a precision better than 1 part in a trillion, cannot see it. That is a remarkably strong confirmation that CPT symmetry, at least here, is holding. And some of it is going to be almost funny in its simplicity. You compare two colors of light, and from that you infer something about the symmetry of time itself. But now the paradox deepens. The more perfectly matter and antimatter agree in these careful tests, the harder it is to understand why the world we wake up in chose one side. If the rules are this symmetric, why did the early universe not leave behind equal islands of matter and antimatter? We honestly don't know for certain, and all of it pushes the next question forward. If the difference is not hiding in these spectral lines, where could it be hiding instead? So let's slow down for a moment and look at what is actually being tested here. When physicists talk about symmetry, they are not just admiring something pretty in an equation. They are listening for a promise the universe is making. Think about a perfectly round table with a painted pattern in the middle. You close your eyes, someone turns the table, and when you open them again, the pattern looks exactly the same. Turning it did nothing to your experience. The table is promising you, no matter how you spin me, I will not change. In physics, the promises are stranger. Change left and right, run time backwards, swap every particle for its antiparticle twin. Symmetry says that if you do all three together, the outcome of any experiment written in the careful language of quantum field theory should be unchanged. It is one of the deepest no matter what statements we have. Here's what we do know, that language, quantum field theory, is not just a set of fancy symbols. It is the mathematics behind the standard model, behind the way electrons move in a wire, behind the way light from a distant galaxy travels to your eyes. PPT is woven into that framework so tightly that giving it up would mean rewriting almost everything. So when CERN traps antihydrogen and measures its spectral lines, they are not just collecting more numbers, they are asking the universe, very politely, whether it intends to keep this promise. Does an antihydrogen atom absorb and emit light at exactly the same frequencies as ordinary hydrogen, down to absurdly many decimal places? Or a tiny crack? The answer so far is that the promise holds. Within the sensitivity of these experiments, antihydrogen and hydrogen sing the same spectral song. And that has a very quiet but very serious consequence. It does not solve the matter-antimatter mystery. If anything, it makes the mystery sharper, because some of it is going to be about where the differences are allowed to hide. Every time a symmetry test comes back, no deviation here, it closes off one more simple story, one more easy place for the imbalance to live. The box around our ignorance gets smaller. Science does not only move forward when we find dramatic differences, it also moves when we confirm sameness to ridiculous precision and are forced to look elsewhere. more remarkable than a broken promise. Sometimes is a promise kept so perfectly that you have to rethink what question you were really asking. If the acronyms are starting to blur a little, that is perfectly fine. You do not need to remember every letter. Let me tell you, what matters is the feeling that we are gently pressing on the rules of the world, asking whether they bend or break. And all of it, every careful comparison of matter and antimatter, is the universe quietly answering here, at least the symmetry still holds. Which means the real asymmetry, the one that chose this particular world for you to wake up in, must be hiding somewhere else. So if the real asymmetry is hiding, the next thing you might ask is whether the mirror itself is cheating. Physicists have a name for this mirror. They call it CP symmetry. The C stands for charge, the way a particle carries positive or negative electric charge. The P stands for parity, the simple idea of left and right, like flipping the world in a mirror. In many situations, if you swap every particle for its antiparticle and reflect left and right, the movie of the process is supposed to look the same. Think about two films laid on top of each other. In one, a particle decays into 3 lighter particles, fanning out in space. In the other, its antiparticle does exactly the same thing, just with opposite charges and mirrored directions. CP symmetry is the quiet claim that, frame by frame, those two films should match. But when mirrors cheat, the films don't quite line up. CP violation is the name for these small mismatches. You start with a particular particle, watch how often it decays into one set of products, and then you do the same for the antiparticle. If nature were perfectly symmetric under CP, the numbers would agree, the same branching, the same probabilities, the same quiet rhythm of events. Instead, in some cases, one side wins by a tiny margin. At CERN, there's an experiment that lives almost entirely inside this idea. It's called LHCb, the Large Hadron Collider Beauty Experiment. And its specialty is watching particles that contain beauty quarks and charm quarks. These are heavy, short-lived pieces of matter that appear for a moment in the collisions and then fall apart. HCb records unimaginable numbers of these decays. Someone has to let the detectors click away for years, collecting data while teams of people sift through the patterns, counting how often one decay path happens for matter and how often for antimatter. It is statistics as a kind of patient listening. And here's what we do know. HCb has seen multiple kinds of CP violation in certain decays of beauty mesons. The matter version really does behave differently from the antimatter version. The imbalance might be only a few parts in 1,000, but it is real. The mirror is not perfect. That discovery is so simple, it's almost funny. You ask, does the universe prefer matter just a little? And the answer in these processes is yes, but then the numbers hit you. The CP violation we have measured is far too small to explain why almost every star, every planet, every atom in your body is matter and not antimatter. The cosmic bias is enormous, the measured bias is tiny. So we honestly don't know for certain where the rest of the asymmetry is hiding. That's where the mystery deepens. Are there hidden processes, perhaps involving new particles we have not yet seen, that twist the mirror much more strongly? And could CERN's ongoing work with antimatter, pushing these comparisons to even greater precision, be about to catch the universe in the act of breaking its own rules in a way we have never witnessed before? So if the universe really is trying to hide the rest of the asymmetry, there's a very simple, almost childlike question you can ask it. If you could hold a tiny ball of antimatter in your hand and then let go, would it fall down or fall up? It sounds like a party trick from a science fiction world, but it has quietly sat at the edge of physics for a long time, bothering people. Because this is not just a question about a falling object. It is a question about whether reality treats matter and antimatter as truly equal, even in the gentle pull of gravity. Here's what we do know. In Einstein's general relativity, gravity is not a special force that cares about electrical charge or about which particle is which. It is the bending of space and time by energy and mass. Anything with energy in it, light, atoms, is supposed to follow that bending in the same way. So on paper, antimatter should fall just like matter. No drama, no upside-down apples. But there was a catch. We honestly don't know for certain until we test it directly with actual antimatter atoms. And for a very long time, no one could think about trying to drop a single positron, the antimatter twin of the electron. It has electric charge. That means the tiniest stray electric field from a wall, from a wire, even from a bit of static on someone's equipment pulls on it enormously. Electromagnetism is something like 1,000,000,000,000,000 times stronger than gravity at that scale. So the gentle downward tug you want to measure is completely drowned in electrical noise. It is so simple. It is almost funny. Gravity is too weak. That's where the idea of antihydrogen becomes important. Take an antiproton, which has negative charge, and a positron, which has positive charge, and bind them together into an atom. The charges balance. From far away, antihydrogen looks electrically neutral, the way ordinary hydrogen does. Now, in principle, you can let this neutral antimatter atom float freely and watch how gravity bends its path. Of course, saying that is easy. Doing it is another experience entirely. You have to make antihydrogen, trap it with magnetic fields, cool it until it is moving slowly enough that gravity has time to act, and then release it gently without kicking it. Some of it is going to be lost, annihilating on the walls. Some of it will escape in directions you did not expect. At CERN, 2 experiments grew out of this very patient idea. AlphaG, an extension of the alpha antihydrogen program, was designed like a vertical trap, so you can see where the released antihydrogen tends to drift down or up. G-bar in a different hall, set out to make antihydrogen so cold that it would almost hover before beginning its fall. In both cases, the aim is beautifully simple. Give antimatter a chance to move under Earth's gravity alone and measure whether its acceleration matches the 9.8 meters per second squared you experience every time you drop something. And if it does not, even by a little, then the mirror we thought we understood may be stranger and more broken than anyone expected. So if you actually want to give antimatter its chance to fall, you need somewhere to drop it. That isn't really a place at all. A kind of invisible cage, made of fields rather than walls, where touching anything means instant annihilation. That's where AlphaG comes in. Imagine a tall, narrow cylinder standing upright in a quiet hall at CERN. Inside it, a handful of antihydrogen atoms are held in place, not by glass or metal, but by carefully shaped magnetic fields that cradle them away from the walls. The whole apparatus is vertical for a reason. If you slowly loosen that magnetic grip, those atoms have to decide, do they tend to escape out of the top or out of the bottom under Earth's gravity? Think about how delicate that is. Each antihydrogen atom is neutral overall, so you cannot just push it around with an electric field. Instead, physicists tune the magnetic bottle that holds them, adjusting its strength, its symmetry, its timing, and then they watch. When an atom finally touches the metal, matter meets antimatter, and there's a tiny flash of annihilation. Detectors around the cylinder record where those flashes happen, top or bottom. By repeating this again and again with different magnetic settings, AlphaG builds up a kind of gravitational fingerprint. If antihydrogen preferred to fall up, more annihilations would cluster near the top. If gravity were dramatically weaker or stronger for antimatter, the pattern of escapes would shift in a clear, statistical way. Here's what we do know within the current blur of uncertainty. The pattern looks very familiar. The atoms fall down. G-bar takes almost the opposite route to the same question. Instead of a tall bottle, It starts with antihydrogen ions, which carry an extra positron. That extra charge lets someone grab them more firmly with electromagnetic fields and cool them to extremely low temperatures until their motion is as gentle as possible. Then, in a carefully timed step, the extra positron is removed. The atom becomes neutral, antihydrogen, and the trap is switched off. For a brief moment, there's nothing left to hold it. It simply falls. You can measure the time between that release and the annihilation when it hits a surface below. Do this many times, and you can infer the acceleration. If our familiar 9.8 meters per second squared were badly wrong for antimatter, G-bar would see it. So far, within their still large error bars, they do not. We honestly don't know for certain whether tiny deviations are hiding in the noise, and some of it is going to be improved as the experiments run longer and the techniques get sharper. But the dream of spectacular anti-gravity for antimatter of antihydrogen rising like a soap bubble is being squeezed into a smaller and smaller corner of possibility. And all of it leaves theorists in an odd position. If antimatter does not float away, yet the universe still prefers matter, then the real strangeness has to live somewhere else. The next clues do not come from watching atoms fall, but from listening to how they shine. And that is where the story turns from gravity to the spectrum of the mirror. So before we go any deeper into that mirror of light and lines, it's worth pausing for a moment, just to look back at the path you've already walked. A very long time ago, at least in the story of physics, there was only the electron. Dirac wrote down an equation to describe it, combining quantum ideas with relativity, and the mathematics quietly produced something unexpected, twin solutions like a reflection hiding in the symbols. Negative energies that at first made no sense at all. Instead of throwing the equation away, he took it seriously. He said, in effect, maybe the mathematics is telling us there's another kind of electron with the same mass but opposite charge, an anti-electron. And not long after, Anderson looked up into the sky, into the spray of cosmic rays in a magnetic field, and actually saw that anti-electron trace its little curve on a photographic plate. The positron, the mirror, had stepped out of the algebra and into the world. From there the idea grew every particle might have a partner, matter and antimatter, and much later in time at CERN people learned how to coax these partners into something more familiar by assembling antiprotons and positrons into whole antiatoms. Antihydrogen, a single proton and a single electron turned inside out. Think about what that means experimentally. You have to trap these fragile antiatoms, keep them from touching ordinary matter, cool them down, and then shine microwaves or lasers on them to see what kind of light they absorb and emit. When Alpha and other teams did this and compared the spectrum of hydrogen and antihydrogen, every line they could measure landed in the same place to an astonishing number of decimal places. Here's what we do know. Within that precision, CPT symmetry is holding. The mirror image behaves, but in another corner of CERN, LHCb watches certain particles decay, and there the mirror flickers. In the way some short-lived particles and their antiparticles transform, there's a tiny preference, a small imbalance called CP violation. It is not huge, but it is real. Matter and antimatter in these processes are not perfectly the same. Then there's gravity. For years, people wondered whether antimatter might fall up, whether the universe was hiding some dramatic twist. The latest freefall tests with antihydrogen show that within current errors, it falls down like everything else. No wild levitation, no easy escape hatch, yet there is still room for subtler effects and deeper puzzles behind them. So you're left with a tension. On one side, almost perfect symmetry, matching spectra, matching masses, matching gravitational pull. On the other, a cosmos made overwhelmingly of matter, with antimatter nearly absent. We honestly don't know for certain why the numbers turned out that way, or where exactly the balance tipped. Some of it is going to be uncomfortable, if you like, neat answers. But let me tell you, this is not a failure. It is a sign that reality is richer than our current stories. CERN's new measurements are like careful brushstrokes, slowly changing the picture, hinting at structures we can feel but not yet fully see. And all of it is leading us toward a stranger question. If the mirror almost holds, where precisely is it finally breaking? So when we say the mirror is breaking, we are saying something very precise, but also very strange. We are saying that a rule we thought was perfectly fair has been caught under very careful observation, showing a tiny preference. Like discovering that a coin you trusted for years lands heads a fraction of a percent more often than tails. Not enough for everyday life, but enough to matter for the deep mathematics of reality. In physics, those rules of fairness are called symmetries. You take the situation, you apply some transformation, and you expect the basic laws to stay the same. Turn left into right. Swap matter for antimatter, run the process backwards in time. If the universe were perfectly symmetric, the probabilities, the outcomes, the underlying numbers would not care. When a symmetry is violated, it means that this expectation quietly fails. You perform the transformation, and the world does almost the same thing, but not exactly. There's a tiny statistical tilt, a hidden bias in the cosmic coin. That is what CP violation is, a combined mirror and matter swap that does not quite preserve the rules. Now add another layer, time reversal. Usually written as T, is the idea of taking a movie of some physical process and playing it backwards. Think about a glass shattering on the floor, pieces flying outward. Run the film in reverse, and you see fragments leap up and assemble into a perfect glass. Your brain knows that second version is wrong. It feels like a trick. But at the microscopic level, with individual particles, the equations often do not care which way you run the film, forward or backward. The mathematics looks the same. When their symmetry holds, a process and its time-reversed twin are equally alive. When D is violated, the universe is, in some subtle way, telling you which direction is past and which is future. Here's where the CPT theorem quietly steps in. It says that if you apply 3 transformations at once, C for swapping particles with antiparticles, P for flipping left and right, and T for reversing time, the combined package must leave the fundamental laws unchanged. So if experiments at CERN show that CP is violated, then there has to be violated too, in just the right compensating way. The universe keeps the full CPT symmetry, but lets CP and T separately be a little crooked. That sounds technical, but let me tell you, it carries an almost philosophical weight, because it means that deep down some microscopic processes in quarks and leptons genuinely distinguish between earlier and later. They are not just victims of entropy or human memory. They build an arrow into time itself, and that arrow brushes against your everyday experience. You remember yesterday and not tomorrow. You age in one direction. You make choices that can influence the future but never the past. We honestly do not know for certain how directly these tiny symmetry violations connect to that lived arrow of time, but here's what we do know. Without a preference for matter over antimatter, you would not be here to wonder about it. So when CERN traps antihydrogen and watches it fall or measures its light with ridiculous precision, it is not only checking exotic particles, it is probing whether the deep rules that give time its direction are exactly balanced or just slightly biased in favor of the reality you inhabit. And all of it is slowly leading to an even sharper question. If time itself is tilted, where does that tilt really begin? Here's what we do know. When physicists talk about the standard model, they are not talking about a single equation scribbled on a board. They are talking about a carefully woven catalogue of particles and forces, a kind of rule book for how electrons, quarks, photons, and their relatives are allowed to behave in this world. It does not include gravity. It says nothing about the slow bending of time around a star. But for everything that happens inside an atom or inside a collider ring at CERN, this framework has been almost uncannily successful. Think about the experience of building something like that. You write down an abstract idea, you let it tell you there should be a Higgs boson or a certain pattern in how particles decay, and then, a very long time ago by experimental standards, you go looking in detector after detector. From LEP to the LHC, you keep finding exactly what the mathematics said you would. Antimatter is folded into this same structure for every particle in the table. The theory quietly insists on an antiparticle twin with the same mass and the opposite charge, HCb alpha, and other experiments have spent years checking this, measuring the light from antihydrogen, timing the decays of strange and beauty quarks, comparing matter and antimatter like two nearly identical pages held up to the light. And again, the standard model passes. The spectrum of antihydrogen matches hydrogen to astonishing precision. The way certain mesons made of quarks and antiquarks flip between states and show a tiny preference for decaying into matter rather than antimatter lines up with a mechanism already written into the theory, a subtle complex phase in the matrix that describes how quarks mix. So on paper there's CP violation. The rules do allow matter and antimatter to behave just a little differently in time. But when you take those numbers and ask a cosmic question, could this tiny imbalance explain why the early universe did not simply annihilate itself into light? The answer is quietly, stubbornly, no, the calculated effect is far too small. By many orders of magnitude, it is so simple. It is almost funny. The better we measure these processes at CERN, the more clearly we see that the built-in asymmetry of the standard model cannot account for the overwhelming excess of matter you see when you look at the night sky. That creates a particular kind of tension. No obvious cracks in the places you can see and touch in the lab. But on the larger scales, a mismatch between what the equations allow and what the cosmos has already done. So physicists do something very human. They start looking for hairline fractures. Tiny deviations in the way antimatter falls or glows or oscillates. That's where some of CERN's latest results become more than just confirmations. They become signposts. Because buried inside those almost perfect mirrors, there may already be the first hint of where the glass finally gives way. So let me bring you back to that first image, a universe standing in front of a mirror. Matter on one side, antimatter on the other. Every particle matched by a perfect twin. You were promised a crack in that mirror, something tiny but unsettling, and now you can start to see where the glass is under stress. It is not the kind of crack people once dreamed about. Antimatter does not float away like a reversed balloon. In CERN's alpha experiment, when they finally let clouds of antihydrogen go and simply watched, those atoms fell down, pulled by Earth just as ordinary hydrogen does. Within the limits of their measurement, gravity behaved. That's important. Because if antimatter had fallen up, the whole story of gravity, and maybe of time itself, would have had to be rewritten overnight. Instead, what CERN found is quieter, more precise, and in a way more disturbing. Think about the symmetries. You met a moment ago charge, parity, time, flip matter to antimatter, left to right, past to future. The deep principle called CPT says that if you do all three at once, the laws of physics should not notice. Here's what we do know. Every time CERN has checked this, comparing the spectral lines of hydrogen and antihydrogen, or the magnetic properties of protons and antiprotons, the mirror holds almost perfectly. Almost. The frequencies match to many decimal places. The shapes of the lines are the same. The numbers line up so well that if there's any difference, it is hiding far beyond our current reach. That near-perfect CPT symmetry leaves fewer and fewer places for new physics to hide. And yet in the same laboratories, another symmetry is already known to fail. In the LHCb experiment, for example, certain particles called B mesons and their antiparticles do not decay in exactly the same way. There's a tiny preference, a small tilt in the statistics. This is CP violation written into the mathematics of the standard model itself. It is real, it is measured, it is not enough. When you run the numbers, that known CP violation cannot explain why the early universe did not simply annihilate into light. The imbalance between matter and antimatter that gave you stars, planets, and the device in your hand is far larger than these little asymmetries can account for. We honestly don't know for certain where the rest of the imbalance came from. So the picture you're left with is delicate gravity. As far as we can tell, treats matter and antimatter the same. CPT symmetry tested again and again in antihydrogen and antiproton traps stands almost untouched. CP symmetry, on the other hand, is cracked, but only by a hair. Not a dramatic shattering. Just faint fractures like stress lines in glass that has been under pressure for a very long time. And all of it points to something beneath the surface. Some deeper structure that the standard model only hints at, where new kinds of imbalance or new particles or new versions of time might be hiding. This antimatter program is, in that sense, a slow, careful search for these hairline cracks, using colder atoms, finer measurements, longer runs. In the next part, let me tell you about a few of those cracks in detail, and how each one might trace the outline of a larger, stranger world behind the mirror. Those cracks in the mirror don't only run through quarks and the heavy, noisy world of protons and neutrons. They also pass through a quieter family of particles that you meet every day without ever noticing. Let me tell you about leptons. In the language of particle physics, quarks build the dense composite things, hadrons, nuclei, the stuff that makes up your chair and your bones. Leptons are their more solitary cousins. The electron is a lepton, so is its antimatter twin, the positron. And then there are the strangest members of the family, the ones that almost refuse to be part of your everyday experience at all, the neutrinos. Think about this while you're lying there, listening to this. Trillions of neutrinos are streaming through your body every second. They come from the sun, from distant cosmic explosions, from radioactive elements deep in the earth. They pass through walls, oceans, whole planets with barely a whisper of interaction. For most of history, no one even knew they were there. Neutrinos are incredibly light, so light that for a long time we treated their mass as exactly zero because it made the numbers easier. So simple, it's almost funny, but nature didn't quite cooperate. We discovered that neutrinos can change their identity as they travel, oscillating between different flavors, electron, muon, tau, in a way that only makes sense if they have a tiny but non-zero mass. And here's what we do know: those oscillations open the door to a new kind of asymmetry. If neutrinos and antineutrinos behave just a little differently when they oscillate, if they violate CP symmetry in their own subtle way, then the early universe might have produced more leptons than antileptons. That imbalance, through a web of reactions, could have been converted into the excess of matter over antimatter we see today. This idea has a name that sounds technical, but is really just descriptive. Leptogenesis, the birth of a matter-dominated universe from a tiny preference in the lepton sector. Most of the direct hunting for this effect happens in other places. Long tunnels filled with detectors in Japan, beams of neutrinos sent through the Earth in the United States and Europe. But CERN is woven into this story. Its accelerators produce intense beams of charged leptons and their antiparticles. Its experiments measure the properties of the tau lepton, of muons, of electrons and positrons, with the same relentless precision that the antimatter teams bring to antihydrogen. Some of it is going to be about quarks, some of it is going to be about leptons, and all of it is part of a single shared effort to map where the symmetries of the standard model begin to fray. We honestly don't know for certain whether the universe shows matter through quark asymmetries, lepton asymmetries, or some intricate combination of both. That's where this becomes less like a single experiment and more like a tapestry. An antimatter program pulls on one thread, neutrino observatories pull on another, and slowly from a decision made a very long time ago, a larger pattern may emerge. In the next part, we'll follow that pattern into one of the most intriguing possibilities for how leptons might have tipped the cosmic scales. So let me tell you where that pattern leads next. It doesn't stay inside the walls of CERN. It stretches outward into the open sky, where antimatter was first seen, long before anyone built a vacuum chamber or a superconducting magnet. A very long time ago, before people even had the word antimatter, they had something else. Cosmic rays. Invisible particles raining down from space, hitting the upper atmosphere with such energy that new particles and antiparticles flicker into existence for a moment, then vanish. That is where the first positrons were actually found, tiny blips in cloud chambers that told someone very quietly that the equations were right. Think about that. The first proof that every particle has a mirror twin did not come from a neat, polished laboratory. It came from the sky simply doing what it always does, smashing things together at ridiculous speeds. Even today, space is still making antimatter for free. Positrons, antiprotons, and other fragments born whenever high-energy particles collide with gas, dust, or starlight. We have learned to listen to these satellites like Pamela and AMS on the space station and balloon experiments drifting high above Antarctica count these antiparticles one by one. They measure how many positrons arrive at each energy, how many antiprotons, and they compare those numbers to what ordinary physics says should happen when cosmic rays hit the galaxy. Here's what we do know. More than once, those counts have come back with a quiet surprise. Too many positrons at certain energies, an excess that does not quite fit the simplest picture of exploding stars and colliding gas. Some of it is going to be ordinary astrophysics we have not fully mapped out yet. But some of it, people have suggested, could be something stranger, like dark matter particles annihilating each other in the halo of our own Milky Way. So simple an idea. It is almost funny. You look up, you count, and the numbers do not add up. Now put that beside CERN. Out in space, everything is hot, fast, and chaotic. Particles race near light speed. Magnetic fields twist them. Shocks and explosions scramble their paths. In Geneva, by contrast, physicists cool antihydrogen atoms to near absolute zero, trap them in carefully shaped magnetic bottles, and watch a single spectral line shift by a billionth. The sky throws antimatter at us. In the lab, we cradle it. These two ways of knowing are not rivals, they are mirrors. Space shows you what nature does on its own with no one watching. CERN shows you what is possible when we patiently coax antimatter into revealing its properties, one transition, one fall under gravity, one annihilation flash at a time. If either side blinks, the story changes a mismatch in the positron spectrum, or a tiny deviation in an antihydrogen measurement would both whisper the same thing. Our picture of reality is not quite finished. We honestly don't know for certain where the first clear crack will appear, but in the next part we'll follow one especially unsettling place those cracks might lead, where antimatter stops being just a mirror and starts to tamper with time itself. So let me tell you a different way of looking at all this talk of cracks and broken mirrors. Imagine you're standing by a lake just before sunrise. The air is cold, the world is quiet, and the water is almost perfectly still. Across from you, a line of mountains rises into the pale sky, and on the surface of the lake you see them again, upside down, as if another world were hanging beneath your feet. For a moment, the reflection is so sharp that you could trace every ridge and shadow, mountain, mountain, sky, sky, more alike than different. Then almost nothing happens. A tiny breeze moves across the surface. Small fish turns just under the water. The mirror does not shatter, it only ripples. The mountains below are still there, but now they waver, they stretch, they blur at the edges. Think about that picture as a way of holding matter and antimatter in your mind. Two versions of the same landscape, so close that you need enormous patience and very careful tools to see any difference at all. Here's what we do know for almost every test we've invented. The reflection behaves. The charges are opposite. The spins are mirrored. The energies line up to an almost comical number of decimal places. It is so simple. It is almost funny. And yet, somewhere in those tiny ripples, the whole history of the universe is hiding. You can feel this pattern in other places in your experience. Your left and right hands matching in structure, failing to overlap. Twins who share the same face but not the same laugh. Patterns in music that repeat but never exactly, always with one note held a fraction longer, one pause that changes the mood. Reality seems to like near symmetries, not perfect ones, almost the same. Not quite. The preference for matter over antimatter may be one of those small imperfections written into the rules a very long time ago. A slight bias in the way particles and antiparticles transform, a tiny imbalance in some early reaction, and suddenly the reflection is not as full as the world above it. If that asymmetry had been different by a hair, there might have been no stars to burn, no planets to cool, no one lying in the dark, listening to someone talk about antimatter on the internet. That's where CERN's experiments fit into the picture. You can think of alpha and LHCb and all the rest as quiet observers on the shore watching the lake. They do not throw stones, they wait. They measure how each little ripple moves, how the reflection of hydrogen falls in Earth's gravity, how an antiparticle's spectrum flickers when you nudge it. Some of it is going to be familiar, most of it will look like a perfect mirror. But every now and then there might be a distortion, a place where the mountains below do something the mountains above would never do. As you drift towards sleep, you can rest in that image of an almost symmetric reality and the sense that somewhere in those ripples, time itself may be bending in ways we are only just beginning to see. If the mirror keeps looking perfect, you might think nothing interesting is happening. But in physics, a mirror that refuses to crack can be just as unsettling as one that shatters. Those mountains above the lake, those antimatter reflections, are tied to a deep rule called CPT symmetry. Very roughly, it says that if you flip charge, flip left and right, and flip the direction of time all at once, the laws of the world should not notice. Many speculative ideas that go beyond our current standard model quietly predict that this rule is not quite exact, that somewhere in some tiny way the mirror is warped. Think about what that would mean in practice. A proton and an antiproton might not have exactly the same mass. An antiproton's magnetic moment, the tiny compass it carries, might tilt just a little differently. Hydrogen and antihydrogen might glow with almost the same colors, but not quite. So simple. It is almost funny. You just compare twins and look for a mismatch. And that is exactly what people at CERN and elsewhere have been doing, with a patience that borders on obsession. They trap single antiprotons for months at a time, weighing their charge-to-mass ratio against protons to something like a part in a trillion. They measure the antiproton's magnetic moment so precisely that if it differed by the width of a human hair compared to the size of the Milky Way, they would notice. They cool antihydrogen atoms, shine microwaves and lasers on them, and listen for the faintest shift in the notes they play. Here's what we do know. Within the sensitivity of these machines, protons and antiprotons match. Hydrogen and antihydrogen sing the same spectral lines. The mirror, as far as we can tell, is flawless. That no difference detected is not a disappointment. It is a discovery with edges. Every time an experiment tightens the bounds and still finds agreement, it carves away huge regions of theoretical possibility. Whole families of models that predicted noticeable CPT violation are simply gone, ruled out by numbers written in careful lab books. So when you hear that CERN has confirmed yet again that matter and antimatter behave the same within some unimaginably small error bar, you are not hearing a non-result. You're watching the space of wild ideas being squeezed, forced to become more subtle, more constrained, more in tune with the quiet stubbornness of the world. Let me tell you, this is an ongoing conversation. Someone writes down an elegant theory that bends time or twists symmetry. Experiment answers, patiently, with another line of data that says, not here, not yet. Antimatter stands in the middle as a precise mirror, repeating the same calm message. If reality breaks its deepest symmetries, it does so very quietly. And all of it is slowly guiding us toward the next place to look, where the mirror might finally just barely ripple. If the mirror only ripples very quietly, you need a very quiet way to listen to it. You need a clock so precise that a change in gravity or a crack in the rules would show up as the tiniest hesitation in its ticking. In modern physics, that clock is an atom. When an electron in hydrogen jumps between two energy levels, it absorbs or emits light at a very specific frequency. That frequency is so stable that you can use it to define time itself, the way someone a very long time ago might have used the swing of a pendulum or the drip of water. Except now, instead of watching a drop fall, you're counting waves of light. Billions of them, every second. Think about what that means. Time, for us, can be anchored to a simple transition inside a single atom, repeated over and over. More regular than your heartbeat. More regular than the turning of the earth. So regular that if the frequency shifts by a part in a trillion, someone notices. Now let me tell you what happens when you build the same kind of clock out of antimatter. At CERN, experiments like alpha cool antihydrogen almost to rest and then shine carefully tuned light on it, watching which colors it will accept. Those colors mark the allowed jumps of its anti-electron, the mirror of the electron in ordinary hydrogen. If matter and antimatter truly share the same internal rules, their clocks should tick in perfect unison. But gravity complicates the story, according to Einstein. Time itself runs differently at different heights in a gravitational field. A clock on a mountain ticks a little faster than a clock at sea level. We have tested this with matter clocks many times. Here's what we do know so far. They all agree with general relativity with astonishing precision. The next step is to lift an antimatter clock into that same gravitational landscape and compare. Does antihydrogen in free fall see time slow down in exactly the same way as hydrogen? Does its ticking stretch and compress with the pull of the Earth, or is there a barely perceptible mismatch? Even a tiny difference would whisper that the equivalence principle, the idea that gravity treats all forms of mass and energy the same, is not quite complete. Future generations of these experiments are being designed with this in mind. Sharper lasers for cleaner spectral lines. Colder antiatoms that drift more slowly, giving more time to watch them fall. Some of it is going to be simple in spirit, almost funny in its clarity. You drop antimatter and listen to its clock as it falls. If the tick rate changes in a way our equations do not expect, then somewhere either gravity or quantum field theory has missed a detail, and all of it feeds into the deepest open question in physics: how to make gravity and quantum mechanics speak the same language. Antimatter offers a complementary probe, a way to ask whether the geometry of space-time, which bends under mass, also bends in exactly the same way under its mirror. If it does, that is a powerful constraint on any future theory. If it does not, then the path to unification will have to pass through that discrepancy. So you can picture the near future as a quiet hall underground where tiny clouds of antihydrogen hang in magnetic traps. Each atom is an almost perfect clock. Its ticking is encoded in faint flashes of light, counted by patient detectors as the atoms rise and fall. Somewhere in those rhythms, there might be a hint that reality is not quite symmetric after all. And just beyond that possibility lies an even stranger question, one that the next experiment is already very slowly preparing to ask. Those faint flashes of light in a vacuum chamber can feel very far away from your own life. But the same matter-antimatter dance that keeps CERN awake at night is already woven into an ordinary hospital corridor. Let me tell you about a machine that quietly uses annihilation to save lives. You may have walked past one without realizing it. It is called a PET scanner, for positron emission tomography, and it looks at first glance like a large white ring with a bed that slides through the center. Very calm, very clinical. Nothing about it suggests that particles are vanishing into pure light inside your body. Here is what actually happens. Someone injects a tiny amount of a radioactive substance into your bloodstream, usually attached to a sugar molecule. As this tracer moves through you, some of its atoms are unstable in a very particular way. They do not just emit ordinary radiation, they emit positrons, the antimatter twins of electrons. Each positron travels only a short distance in your tissues before it meets an electron. When they touch, there's no gentle compromise, they annihilate. Their mass is converted into energy, and that energy appears as two gamma rays, two very high energy photons, flying off in almost exactly opposite directions. So simple, it is almost funny. Two particles go in, two flashes of light come out around you. Hidden in the ring of the scanner are rows of detectors waiting for those pairs of flashes. When two gamma rays arrive at almost the same time on opposite sides, the machine notes that coincidence. One event, one tiny act of matter-antimatter disappearance. By collecting millions of these events, the scanner slowly reconstructs where in your body the annihilations were most likely happening. Bright regions in the final image show where the tracer accumulated, where cells were hungriest for sugar, where metabolism was unusually active. That is where a tumor might be hiding. That is where a patch of brain might be working overtime or falling strangely silent. Think about that for a moment. The same basic process that shows up when cosmic rays hit the upper atmosphere, the same process that CERN studies with elaborate detectors, is also what lets a doctor see the living chemistry of your brain. Gamma rays from annihilation, caught, counted, and turned into a picture. More remarkable than fire, more remarkable than language, even if you're the patient on the bed. And PET scans are not the only place antimatter steps quietly into everyday technology. Positrons are used to probe the structure of materials, slipping into solids and revealing tiny defects by the way they annihilate. Antiprotons help with some of the most precise measurements of fundamental properties, numbers that feed back into the devices and standards that shape your world. Antimatter is not just a theoretical curiosity, it is a practical tool. So while you rest, while you sleep, the strange mirror world is not entirely elsewhere. It is in the scanners that diagnose illness, in the experiments that test new materials, in the measurements that keep our description of reality honest. And all of it is quietly preparing us for the next question. When we turn from using annihilation as a tool to asking what it really says about the deep imbalance between matter and antimatter in the first place. So now you can imagine the next step. We stop treating annihilation as just a useful tool, and we start treating the whole universe as a very old crime scene, a crime scene from a very long time ago. Think about the beginning. If our best equations are even roughly right, the Big Bang should have made matter and antimatter in almost perfect balance, particle for particle, like rows of matching footprints in fresh snow. But when you look around your world now, you do not see that mirror. You see stars, planets, all built from matter, with only a whisper of antimatter turning up in cosmic rays and in careful experiments. Most of the evidence is gone. The original matter and antimatter met, annihilated, and left behind a bath of background light and a tiny excess of matter, the residue we live in. It is as if someone scrubbed the floor, painted the walls, and waited 13.8 billion years. And yet, some of it is going to be recoverable, not in the sky, but in the lab. That is where CERN becomes less like a factory and more like a forensic lab. The accelerators slam protons together at enormous energies to briefly recreate the temperatures of the first instance, making pairs of particles and antiparticles the way the early universe did. The antimatter traps, holding antihydrogen for hours at a time, are like delicate glass vials where you can preserve a trace chemical from the scene without letting it touch the air. For a moment you have a tiny sample of that vanished anti-world freshly made. Then the measurements begin, every spectrum line from antihydrogen, every decay pattern of an antiparticle, every test of how antimatter falls in Earth's gravity is treated like a fingerprint or a faint footprint in dust. HCB's studies of how certain particles and antiparticles decay just a little differently. Alpha's readings of antihydrogen absorbing and emitting light at almost exactly the same frequencies as hydrogen. These are like comparing two nearly identical shoe prints under a magnifying glass. Here's what we do know. Each extra decimal place of precision rules out whole families of stories about what really happened. Physicists call it the baryon asymmetry problem, but you can hear it as a very strange whodunit. What process or combination of processes in those first fractions of a second tilted the balance so that when the great mutual annihilation was over, one extra matter particle was left over for every billion that vanished? Was it a new kind of interaction, a subtle breaking of symmetry, a twist in how time itself behaves? We honestly don't know for certain. What we do know is that many suspects have quietly been eliminated. Whole simple ideas about antimatter falling up or wildly different spectra are no longer allowed by the data. And all of it is slowly steering us towards stranger possibilities, faint shapes at the edge of the reconstruction. In the next step, we will follow those shapes and ask what it really means if the universe's missing anti-world is pointing to new rules of reality we have not yet written down. Those faint shapes at the edge of the reconstruction are not just about particles and equations. They are very quietly about you. Let me tell you something simple that is almost funny in how severe it really is. If, a very long time ago, the Big Bang had created matter and antimatter in exactly equal amounts, and if they had behaved in exactly symmetric ways, then almost everything would have met its opposite and vanished, not in some poetic way, literally annihilated, leaving behind a thin bath of radiation, a smooth glow, and not much else. No long-lived stars, slowly burning for billions of years. No planets cooling and cracking. No chemistry patiently exploring combinations of atoms. Just light, expanding and fading. Here's what we do know. For every 10 billion particles of antimatter in the early universe, there were about 10 billion and one particles of matter. that tiny excess, that one extra in 10 billion, survived the great mutual erasing. Everything you have ever seen, every star you have ever noticed, every grain of dust drifting in a beam of sunlight is built from that leftover. Think about that for a moment, your body with its quiet electrical signals and its warm pulse, your memories, the way 1 year of your life blurs into another, the way a single afternoon can stay sharp for decades. Your current moments of rest, listening to someone talk about antimatter on a screen, all of it traces back to that slight imbalance in the beginning. We honestly don't know for certain why the numbers came out that way, why there was that extra one, why the universe did not simply erase itself in a flash and move on. That's where CERN, with its cold machinery and bright tunnels, enters the story. On the surface, it can feel very far from ordinary experience. Superconducting magnets, vacuum pipes, detectors the size of buildings, catching brief flashes when matter and antimatter meet. But in a quiet way, what they are doing is trying to understand the conditions that made personal experience possible at all. When alpha holds antihydrogen in a trap, or LHCb measures a tiny preference for matter over antimatter in the debris of a collision, it is really asking, what had to happen so that a long time later someone could sit in a dark room and wonder about their place in the world? There's a pattern interrupt here if you want one. The next time you feel very small in the face of the cosmos, you can gently flip the picture. Without that almost imperceptible asymmetry, there will be no one to feel small, and no cosmos filled with structure to feel small inside. It does not have to be unsettling, it can be calming even. You are part of a vast, delicate pattern that physics is only beginning to describe, a pattern that survived annihilation by the narrowest of margins. And as CERN slowly maps the rules that allowed that survival, it is also indirectly mapping the prehistory of your own quiet existence. In the next step, we will follow that thought outward again and ask what happens if the same fragile imbalance is still shaping the future of the universe, not just its beginning. So now imagine this. The universe that survived annihilation by the narrowest of margins might not be the only game in town. Not in the sense of science fiction, multiverses with infinite copies of you. Something quieter, a shadow world, made of particles that barely notice us, flowing through the same space and time, almost never leaving a mark. Physicists call these possibilities hidden sectors. You can think about them as extra chapters in the book of nature, written in the same mathematical handwriting, but in ink so faint that almost no experiment can see it. The particles in a hidden sector could have their own forces, their own versions of light and matter, interacting with our world only through the tiniest cracks. Let me tell you one version of this idea that people take surprisingly seriously. It is called mirror matter. In these models, every particle you have heard of in the standard model has a partner in a parallel sector, a mirror electron, a mirror proton, a mirror photon. The mirror particles talk to one another strongly, making mirror atoms and mirror stars, but they talk to us only in whispers, maybe through gravity, maybe through a very weak mixing of forces. If that sounds like a story someone might have told a very long time ago about spirits and reflections, the modern version is much more precise. You can write down equations, count the possible interactions, and ask whether mirror matter could be what we call dark matter, or whether a slight mismatch between the two sectors could help explain why matter won over antimatter in the beginning. Here's what we do know. None of this is established fact. We honestly don't know for certain whether any hidden sector exists at all. There is no direct, unambiguous signal of mirror atoms drifting through the detectors at CERN. What we do have are carefully drawn boundaries. If such a shadow world is there, it has to obey the limits that real experiments have already set. That's where antimatter comes back in. Any tiny deviation in the way antimatter behaves compared with the clean predictions of the standard model, could be a hint that something unseen is tugging on it. A slightly shifted spectral line in antihydrogen, a minuscule difference in how it falls in Earth's gravity, a barely measurable asymmetry in decays at the LHCb experiment. Each of these would be like a fingerprint pressed against the glass from the other side. Most of the time, the answer so far has been beautifully boring. Within the current precision, antimatter falls like matter, shines like matter, obeys the same mathematical rules. It is almost funny how stubbornly nature refuses to give up her secrets. And all of it means that the real work right now is slow, tightening bounds, refining models, waiting patiently to see whether the next decimal place in a CERN measurement will stay perfectly ordinary, or whether in that last quiet digit a mirror world will finally blink. So when that last quiet digit refuses to misbehave, you might wonder what any of this has to do with your own experience of time simply moving forward. There was a moment earlier when we talked about T-symmetry, the idea that many of the equations in particle physics barely flinch if you reverse the direction of time in them. Run the process backwards, change a few signs, and the mathematics looks almost unchanged. Almost. Because in a few very special reactions, especially those tangled with CP violation, the film does not quite run the same way in reverse. The probabilities shift. The balance leans on the microscopic stage. Time reversal symmetry is ever so slightly broken, and that is already something quietly astonishing. But then you look up from the equations and notice your coffee cooling on the table, the ice melting in a glass, your memories lined up neatly behind you rather than ahead. Your whole world seems to have a very clear before and after. And that arrow of time feels nothing like a tiny correction in a CERN data set. To connect those scales, let me tell you about entropy. In the language of thermodynamics, entropy is a way of counting how many microscopic arrangements could give you the same big picture state. Many ways for the molecules to be jumbled, very few ways for them to be perfectly ordered. More microstates means higher entropy. The second law of thermodynamics says that statistically entropy tends to increase, not because the universe has a preference in any moral sense, but because there are overwhelmingly more ways to be disordered than ordered. Shattered glass, cooled coffee, mixed cream, the movie where they unshatter themselves is allowed by the equations, yet so rare that you will never see it. Here's what we do know. This statistical tilt gives us a macroscopic arrow of time. It tells you which direction is future in your everyday experience. It is the direction in which entropy increases. The strange thing is that this arrow depends on a boundary condition, on how the universe began. A very long time ago, the early universe seems to have started in an extraordinarily low entropy state, smooth and simple compared to the wild clumpiness of galaxies and stars you see now. At the same time, it seems to have chosen matter over antimatter by a tiny excess. Two asymmetries written into the beginning. Think about that. The low entropy beginning sets up the thermodynamic arrow. The matter-antimatter imbalance sets up a cosmic history in which something survives to notice that arrow at all. Both are like initial instructions whispered at the start that shape everything which follows. We honestly don't know for certain whether the CP and T violations seen in experiments like LHCb are deeply tied to that grand thermodynamic story, or whether they are parallel quirks of the same underlying mathematics. Some of it is going to be ordinary bookkeeping, some of it might not be. What they do show very clearly is that the fundamental laws are not completely indifferent to the difference between past and future. There is a faint asymmetry written directly into the rules, not just into the starting position of the game. And that's where CERN's antimatter experiments become more than a technical achievement. They are small, controlled attempts to ask the universe why time seems to flow, why you remember yesterday but not tomorrow, why causes feel different from effect. Because if even a single property of antimatter had leaned the other way, the whole story of increasing entropy, of stars forming, of you listening to this right now, might have looked utterly different. The real question, waiting just beyond these careful measurements, is whether that story is finished or whether time itself is still hiding a deeper script that we have only begun to read. So when you hear about CERN weighing antihydrogen or timing the fall of antimatter in a vacuum tube, it can feel very far away from the quiet room you're in right now. But let me tell you, the consequences are already sitting on your nightstand. Think about that phone slowly charging beside your bed. Inside it, electrons flow through tiny pathways cut into silicon, obeying quantum rules that were written down a very long time ago to explain light atoms and, yes, the existence of antimatter. The same mathematics that predicts a positron also predicts how a transistor switches, how a screen glows, how information moves from someone else's tower of metal and cables to the small rectangle in your hand. Move your attention up, beyond the ceiling, past the clouds to the GPS satellites quietly tracing their paths around the Earth. Their clocks are not just good, they are astonishingly precise, corrected for both their speed and their height in our planet's gravitational field. Here's what we do know. Those corrections depend on constants, on numbers in our equations that tell us how fast light travels, how strongly particles interact, how time itself stretches. Precision tests with electrons and positrons, protons and antiprotons feed back into those numbers, shaving away uncertainty so that when your map says you are on one side of the street and not the other, it is telling the truth. In a hospital, an MRI machine hums softly, building detailed images of the human body from the faint whispers of spinning atomic nuclei. The power grid that keeps that machine alive, that keeps your room lit, is synchronized across continents by clocks that must agree to absurdly small fractions of a second. Those clocks, in turn, are tested against atomic transitions whose behavior depends on the same fundamental interactions that CERN is probing when it compares matter and antimatter spectra. If a constant were even slightly different, the timing of every signal in a communication network would drift, slowly at first, then catastrophically. So when researchers trap antihydrogen and watch how it responds to gravity or to electromagnetic fields, some of it is going to be about pure curiosity. But some of it is about tightening the bolts on the invisible scaffolding that holds all this technology together. If antimatter were to fall up or radiate at a slightly different frequency, we would have to rewrite the instructions for building semiconductors, for designing reactors, for navigating spacecraft through the deep dark between worlds. And all of it comes back to you, sitting in a room that looks solid and familiar, resting on an architecture you cannot see. Your body, your devices, the cables in the walls are arrangements of particles and symmetries that someone is patiently mapping and testing in underground tunnels. The next time you glance at a screen or feel your heartbeat echoed on a monitor, you're touching the same web of laws that decides how antimatter should behave. The only question is whether that web is complete, or whether the next tiny discrepancy will tug the whole picture into a new shape. If you could follow that tiny discrepancy, that tug on the web of laws down into the tunnels at CERN, you would not find drama. You would find someone in a quiet control room watching numbers crawl across a screen. A typical day, if there's such a thing, begins long before anything exciting happens. Let me tell you how it often looks. You badge in, walk past concrete walls and thick doors, and make your way to a room full of monitors. On one screen, the temperature of a superconducting magnet. On another, the pressure of an ultra-high vacuum chamber where a few dozen antihydrogen atoms might appear. On another, lines of code compiling slowly. Most of the time, nothing obviously magical happens. You write software to sift through yesterday's data. You check that a laser is tuned to exactly the right frequency. You adjust a calibration curve so that a tiny blip in a detector is recorded as the right amount of energy at the right time. Then you wait, runs begin, antiprotons circulate, you're cooled or coaxed into a trap. The system tries to assemble neutral antihydrogen and hold it in a magnetic bottle. You watch for rare events, maybe 1 in a million collisions, that leave a distinctive pattern. Most runs end with no triumphant shout, just a little more data, a slightly better understanding of background noise, error bars pulled in by a fraction. Think about building the apparatus that makes those runs possible. A single antihydrogen trap can take years, even decades, to bring from idea to stable operation. Vacuum seals leak, magnets quench and lose their superconductivity. An unexpected hum from a power supply leaks into the detectors and mimics a signal. Entire months can be spent chasing a piece of electronic noise that turns out to be a loose connection. It is so simple, it is almost funny afterwards. And through all of it, the goal is to measure something almost absurdly small. Fractions of a percent in how often one decay path is chosen over another. Parts per trillion in the spacing of spectral lines of antihydrogen compared to hydrogen. Here's what we do know. Any real difference there would shake our picture of the universe. But to see it, you have to be willing to stare at what looks like nothing for a very long time. This is not the kind of work that rewards impatience. It is quiet persistence, repeated thousands of times, running code, realigning optics, rethinking an assumption. Some of it is going to fail. Some of it will only tell you that matter and antimatter still match, at least to the precision you can reach today. As you listen now, following a slow, detailed story about invisible particles and distant experiments, you're practicing a version of that same patience. You're letting your mind hold an idea gently, without rushing to a conclusion, and all of it, the long nights, the tiny signals, the calm attention you're giving to this, adds up to a different way of being in the world. Because somewhere, perhaps tonight, another run will finish. A new line of numbers will appear, and buried inside them may be the first hint that the mirror between matter and antimatter is not quite as perfect as we thought. So let me tell you something quietly unsettling. We keep saying that the great cosmic mystery is, why is there more matter than antimatter? It sounds neat. It feels like a question about fairness, about balance, about a universe that somehow cheated on the exam. But think about what that question is secretly assuming. It assumes that the natural, reasonable, almost morally correct state of the early universe was a perfect 50-50 split. Half matter, half antimatter, like two sides of a carefully weighed scale. It assumes that the laws of physics a very long time ago were trying to be fair. That is a very human way to think. We like symmetry. We like equal shares. We like the idea that if there is a particle, there must be an antiparticle, and that the world should give them both the same chance. More remarkable than fire, more remarkable than language even, is our instinct to project that sense of fairness onto the cold mathematics of the cosmos. But the universe does not owe us that feeling. Here's what we do know. The equations that gave Dirac his prediction of antimatter are symmetric. For every electron, there's a positron in the mathematics. For every quark, an antiquark. If you start with perfectly symmetric conditions, you really do expect almost perfect cancellation. Matter and antimatter meet, annihilate, and leave behind only light in that picture. The strangest question is not, why is there more matter than antimatter? The strangest question is, why is there any matter or antimatter at all, once the first furious moments have passed? Why did anything survive the fire? That is where another idea quietly walks in. Maybe the puzzle is not about the rules themselves, but about the way the game was set up at the beginning. initial conditions, the way fields rolled and settled as the universe cooled, phase transitions like water freezing into ice that favor one tiny imbalance over another. You can imagine some field in the early universe, not a particle you could hold, but a smooth ocean of value stretching everywhere. As the temperature dropped, that field might have tipped, just slightly, toward configurations that made a few more particles than antiparticles. No deep principle broken, no cosmic crime, just the natural outcome of how the landscape was shaped. From far away, it feels almost ordinary. CERN's antimatter experiments are, in a way, asking which story we are living in. Are we seeing hints of entirely new interactions that twist the symmetry between matter and antimatter? Or are we watching the consequences of known physics, playing out through the specific history of our universe with no extra rules added? We honestly don't know for certain, not yet. Some of it is going to be in the data they already have. Some of it will need new machines and new patience. And all of it depends on whether we are even phrasing the question in a way the universe is willing to answer. So for a moment you can hold the question itself lightly, as if it were a pebble on your palm. Maybe progress this time will come less from a dramatic new answer and more from slowly realizing that the question we started with was just a little bit off. So if the question might be a little bit off, the next thing CERN wants to do is very simple and also very ambitious. They want to ask it again, but more quietly. That means changing the machines themselves. Over the next years, the accelerator complex that feeds the antiproton decelerator is being upgraded, so that every second more antiprotons are born, slowed down, and delivered to the people who spend their time coaxing them into tiny electromagnetic bottles. More particles, held for longer, cooled to lower and lower temperatures until their motion is so gentle it is almost an idea rather than a thing. Think about what that buys you. If today you can hold a few dozen antihydrogen atoms and listen to one particular spectral line, tomorrow you might hold thousands, whispering in many different frequencies at once. Alpha and A-trap are already measuring the light that antihydrogen absorbs and emits, comparing it to ordinary hydrogen with absurd precision. With better trapping and cooling, they plan to push that comparison another order of magnitude, then another. Each extra decimal place is like sharpening the focus on a cosmic microscope. The same quiet arms race is happening with gravity. Experiments like Alpha G and G bar are redesigning their setups so that antihydrogen can be released in a cleaner, colder free fall, watched as it drifts under Earth's pull. Does it accelerate at exactly 9.8 meters per second squared to every measured digit? Here's what we do know so far. Within our current resolution, antimatter falls down, not up. But with more antiprotons and better control, the next decades will let them ask that question again in a softer voice, listening for a tiny mismatch. Then there are the fundamental properties that sound almost like characters in a story, magnetic moments, charge to mass ratios, the way a particle spins in a magnetic field. CERN's dedicated experiments on antiprotons plan to compare these quantities with their matter twins more closely than ever, chasing differences that, if they exist at all, may hide in the 12th or 13th decimal place. Some of it is going to be so simple it is almost funny. You flip a particle in a trap, you watch how it precesses, you write down numbers, and all of it is a test of whether the mirror between matter and antimatter really is flawless. Beyond that, new ideas are slowly coming into focus. Physicists are beginning to imagine interferometers built from antimatter, where antiprotons or antihydrogen atoms behave like waves, overlapping with themselves. Tiny shifts in those interference patterns could reveal minute differences in gravitational or electromagnetic fields, turning antimatter into a kind of ultra-sensitive antenna for the structure of space around you. We honestly don't know for certain where the first crack would appear, if it appears at all. But that's where the next decades are headed, not toward louder discoveries, but toward a long, patient conversation with reality, in which CERN keeps asking the same questions over and over in a lower and lower whisper. Until maybe reality clears its throat and says something we did not expect. And if that happens, the real shock will not be in the numbers they write down, but in what those numbers force us to rethink next. So let me tell you, this is the quiet place where the title of this video finally comes due. What CERN has broken is not a single dramatic law of physics, but something softer and closer to home, the comforting picture that matter and antimatter were going to be a simple mirror story, with a simple reason why you and I only ever see one side. For a long time you could get away with that story. Every particle has a twin, same mass, opposite charge. Put them together, they vanish in a flash of light. Elegant, clean, so simple, it is almost funny, but then you follow what CERN has actually done, slowly over years. You watch antihydrogen trapped and cooled until its spectral lines can be compared to hydrogen, digit by digit. You watch LHCb count tiny differences in how particles and antiparticles decay, a few extra events here, a few missing there. You watch alpha G let antihydrogen fall to see if it drifts down, not up. And the answer is not the neat fairy tale. Here's what we do know. In experiment after experiment, antimatter keeps matching matter with astonishing precision. The energy levels of antihydrogen line up with hydrogen to many decimal places. Its response to electric and magnetic fields looks the same. When you drop it, within current uncertainties, it falls down like everything else. At the very same time, those decay patterns show small but real asymmetries, the CP violations that say the mirror is not perfect. There's a tiny bias hidden in the way some particles turn into others that slowly nudges the universe away from equal parts matter and antimatter. So the picture has become more complex, not less. Almost all the easy answers to the matter-antimatter puzzle have been quietly closed. We can no longer honestly say, as popular accounts once did, that antimatter is just matter with opposite charge, and that is the end of the story. Instead, you have to hold a layered reality in your mind where near symmetry and subtle imbalance coexist like two almost identical melodies that occasionally fall out of step. Think about what that does to your inner model of the world. A very long time ago, you might have imagined a simple mirror universe made of antimatter, galaxies and people running backward in some cosmic reflection. Now you have to imagine something stranger, a universe whose deepest rules almost balance but not quite, and whose very existence depends on that tiny failure of perfection. Some of it is going to be uncomfortable. It means accepting that the foundations are more intricate, less tidy than we might like. But it is also a gentler kind of breaking, like cracking open a shell to find a more complex structure inside. CERN's antimatter work is breaking our oversimplified pictures and inviting us into a deeper, slower conversation with reality. And all of it leaves a question hanging in the air, waiting for the next section. If the old mirror story has shattered, what new picture of the universe are we slowly being pushed toward? So when that old mirror story shatters, you're left holding something very strange in your hands. Not a broken gadget, a pattern that began as symbols on paper and now echoes through a 27-kilometer ring under the French and Swiss countryside. Let me tell you how abstract this used to be. CPT, CP charge and parity and time reversal were once just ways of saying, in the language of mathematics, if you flip this and this and this, the equations stay the same. Lines of symbols obeying rules. A very long time ago, that would have been the end of the story. Beautiful symmetry. No evidence, but someone built accelerators. Someone trapped anti-hydrogen in magnetic bottles at CERN. Now those quiet letters, C, P and T, are not only in notebooks, they are being asked questions by real particles and antiparticles racing through real tunnels. Here's what we do know. When CERN measures the spectrum of antihydrogen, the colors it wants to absorb are so far the same as hydrogen. When LHCb measures CP violation in decays of strange and beauty quarks, the numbers almost but not quite match the simplest expectations. The symmetries are there, and they also slip. That tiny slipping matters. Because these rules and their violations quietly decide which particles live long enough to do anything interesting. They decide which reactions are allowed, which decays happen quickly, which combinations of matter can survive more than a heartbeat after the Big Bang. If CP symmetry were perfect, matter and antimatter would have cancelled almost exactly. No leftover, no galaxies, no you. Think about your bed for a moment. The feeling of weight as you lie down, the resistance of the mattress, the solid frame under it. That solidity is atoms arranging themselves into lattices, electrons refusing to occupy the same state, forces that exist only because certain particles did not vanish in the first second of cosmic time. The chemistry of your brain, the way a thought slowly forms and fades, is possible because protons are stable and electrons do not suddenly decay into something else halfway through a sentence. Even your sense that time flows in one direction, from earlier to later, is entangled with these asymmetries between matter and antimatter. So by listening to a slow story about antimatter, you have not really been visiting some exotic, separate world. You have been walking a little dreamily through the blueprint of your own existence. Some of it is going to be like a half-remembered dream in the morning, names of experiments, acronyms, details of decays, but the outline remains. There are deep rules, they could have been different. And all of it from those rules flows into the room you're in right now. Here is the pattern interrupt. The humming machinery at CERN and the quiet object on your nightstand, the phone, the lamp, the glass of water, are not opposite. They are two ends of the same chain of cause and effect, stretched from the first fractions of a second after the Big Bang to this exact moment. In the next part of the story, we will follow that chain a little further and ask what kind of universe you're actually living in, if its most basic mirror is cracked but not completely broken. So let me tell you where that cracked mirror has taken us. We began a very long time ago in the story with something that was not a laboratory at all, but an equation on paper. Dirac wrote down a new kind of wave equation for the electron, one that respected both quantum rules and Einstein's relativity. And when he solved it, there were these strange negative solutions like shadows of the usual ones that did not seem to belong. At first they looked like a mistake. Then someone noticed that if you read them differently, they described a particle just like the electron, only with the opposite electric charge. Not less real, just mirrored. A few years later, Anderson watched a thin silver track in a cloud chamber slice through a magnetic field the wrong way, curving up instead of down, and the ghost in Dirac's mathematics suddenly had a name, the positron. From there the idea grew quietly but firmly. Every particle of matter, you were told, has an antiparticle twin. Proton, antiproton, electron, positron, neutron, antineutron. Same mass, same basic structure, but opposite charges and quantum labels facing each other across an invisible line. Now think about the beginning of the physical universe itself. In the first split seconds after the Big Bang, the picture we use is incredibly simple. So simple, it is almost funny. For every particle of matter, there was an antiparticle. They met, they annihilated, they turned into light, over and over again. A cosmic version of +1 and -1, cancelling to 0. And yet somehow, Not quite. Here's what we do know. For reasons we honestly don't know for certain, there was a tiny excess of matter. Out of maybe 1 billion pairs, one lonely particle in 1 billion did not find its mirror partner. Those leftovers cooled, clumped, and eventually became stars, planets, cities, and you lying here listening to this. That imbalance is where CERN enters the story. Instead of just trusting the equations, people there learn to make antimatter on demand. They smash ordinary protons together so violently that the energy condenses into new particles, including antiprotons. They slow those antiprotons down, collect them and bring in positrons from radioactive sources. Piece by piece, they assemble antihydrogen, the antimatter twin of the simplest atom. Those fragile atoms are held in magnetic traps, bottles made of fields instead of glass, so they never touch the walls and vanish. Inside those invisible cages, scientists shine microwaves and lasers on antihydrogen and watch what kind of light it absorbs and emits. They gently let it go and time how it falls. Then they compare everything to ordinary hydrogen to the way that ordinary matter falls in Earth's gravity. So far, the results draw a very delicate picture. Wherever our deepest symmetries, say matter and antimatter, should match, they match to astonishing precision. The colors of the light, the basic pull of gravity, the way the atoms respond to fields. And yet in other corners of physics, in rare particle decays and subtle imbalances, we do see small asymmetries, tiny tilts in the rules that just might explain why matter won. You do not need to remember the acronyms or which experiment did what. Some of it is going to be a blur, and that is completely fine. What matters is the shape of the story, from an odd minus sign in an equation to a silver track in a cloud chamber, to whole factories of antimatter, and now to the quiet room you're in, where this entire chain of ideas is simply part of your experience of the world. So now, with that whole chain of ideas gently resting in your mind, we arrive at the most honest part of the story. There's a great deal we still do not understand, and that is all right. Here's what we do know. The equations that gave us antimatter say that in the beginning, the Big Bang should have produced matter and antimatter in almost perfect balance, twin oceans of particles and antiparticles. Yet when you look around your room or think about the Earth or the distant galaxies, you see matter everywhere and hardly any antimatter at all. The exact origin of that imbalance, that tiny tilt in the numbers that let anything exist, remains a quiet mystery. We honestly don't know for certain why the universe chose this side. Physicists give it a name, the matter-antimatter asymmetry, and they look for clues in delicate effects called symmetry violations, where particles and antiparticles do not behave as perfect mirror images. Experiments at CERN, like LHCb, watch particles flicker between states and measure the faintest preference for one direction of time over another. Some of it is going to be about how nature treats past and future, and whether our familiar idea of causality is only an approximation. But the full implication of those tiny differences is still out of reach, like a star that is visible but far too distant to visit. There might be hidden sectors as well, whole families of particles that barely touch our world. Someone at CERN, a very long time ago, compared it to hearing a faint melody behind a wall and trying to reconstruct the orchestra. Maybe some of the missing antimatter slipped into those unseen arrangements. Maybe it did something even stranger. For now, we honestly don't know for certain, and all of it can simply remain a gentle question in the background. Think about the accelerators and detectors as you lie here. Circles of magnets buried in the ground, vacuum pipes stretching for kilometers, silent caverns filled with electronics that blink and listen. While you sleep, beams will still be circulating, colliding, whispering information into those machines. Someone's code will sort through the flashes, counting events the way people once counted pebbles, which is almost funny when you remember how this all began. The universe keeps answering in tiny increments, even when you're not watching. You do not have to solve any of it tonight. It is not your job to decide where the missing antimatter went, or whether time itself is slightly skewed. You can let these questions be like constellations, clear enough to recognize, too far to touch. Spaces where future ideas will bloom in experiments not yet designed, in notebooks not yet opened, in minds that are, at this very moment, still asleep. So you can let go of the effort to follow every detail. Let the story of antimatter drift to the edge of your awareness, like a low, distant hum at the end of a long day. Because the truly surprising part, the part we are slowly approaching, is what happens when you ask whether this strange, lopsided universe could have turned out differently at all. There's a quiet paradox hiding there. Your life feels so solid, so given, and yet it hangs on the outcome of ancient events you never saw, shaped by particles you will never touch. And if tomorrow that thought drifts back to you, even faintly, you might feel a small pull to see what this strange story actually looks like. If that happens, let me tell you a simple place to begin. You could, at some unhurried moment, look up images of a cloud chamber. Not to study, just to see tiny white threads curling and branching, each one a record of something invisible brushing through our world and leaving a trail. It is so simple, it is almost funny, that a box of vapor and a few charged particles can make the unseen draw its own handwriting in front of you. Or you might search for pictures of anti-hydrogen traps, shiny metal rings, nested like careful jewelry, vacuum chambers, soft glows of instrumentation. Some of it is going to be unfamiliar machinery, of course, but you do not need to know every name. You can simply remember that inside those devices, atoms that should have vanished a very long time ago are being held gently in place so that someone can ask them how they behave. Think about the tunnels under CERN, long concrete corridors curving out of sight, cables and magnets stretching into the distance. You could glance at a photograph of the Large Hadron Collider ring or the Alpha experiment and let it register that, somewhere under fields and villages, people are patiently dropping little pockets of antimatter to see whether they fall down like you do. If you ever feel like going further, you might read a short article or watch another quiet video about antimatter or the Standard Model or the Big Bang. Not as homework, more like continuing a soft conversation with reality, one that you can pick up and put down whenever you like. Here's what we do know. Every time you return to these ideas, even briefly, your picture of the world gets a little wider, a little stranger, and a little more connected. And all of it can stay with you in very ordinary moments. You can be drinking coffee, feeling the warmth of the cup in your hand, and remember that your existence depends on a tiny imbalance in the early universe, a slight preference for matter over antimatter. You can be walking outside, hearing traffic and birds, and recall that by Wright's number, say, it all might have cancelled out into light. You can look up at the night sky and quietly think, we honestly don't know for certain why there is something rather than nothing, and yet here you are breathing under the stars. Even if by tomorrow the names and details blur, that is completely fine. Some part of your mind has brushed against the deep structure of the cosmos. That contact is already enough, so you can let these possibilities rest now. They are not going anywhere. The universe will still be unfolding. Whenever you wish, you can return to them as slowly as you like and ask again how this lopsided, luminous reality came to be. So let me tell you a different way to hold all of this just for tonight. Imagine that the tunnels and detectors are very far away now, as if they were on another shore. Around you, there's only a calm, dark sea. The air is cool. The sky is clear above you, a wide field of stars. Below you, the water, reflecting them almost perfectly. You are lying on your back, gently floating. There is no engine, no destination, only the slow rise and fall of the surface carrying you. The stars above look sharp and steady. Their reflections below shimmer, almost the same, but not quite. The tiniest ripples bend them, stretch them, break them into soft threads of light. Think about that image for a moment. The stars above are matter, the familiar world, you, the earth, the machines at CERN, every atom that ever formed in a star a very long time ago. The reflections below are antimatter, the almost twins that the equations of physics whisper about, and the ripples between them, those little disturbances that spoil the perfect mirror, are the asymmetries that let anything exist at all. Here's what we do know. If the sea were perfectly still, if every reflection matched every star exactly, matter and antimatter would have cancelled each other with ruthless precision. No galaxies, no chemistry, no one to float here and wonder about it. It is only because the water is not perfectly calm, because there's the slightest tremor in the symmetry, that the universe had room to become complex and alive. Your thoughts right now can be like those ripples. A worry that rises, then fades. A memory that stretches a little, then smooths out. You do not have to still the entire ocean of your mind. That would be impossible, and in a way it would erase the very texture of your experience. You can simply notice that each thought is a small pattern on a much larger, mostly quiet surface. If one thought feels sharp like a bright star, notice its reflection too, a softer echo below, already blurring at the edges. You honestly don't know for certain which one will last longer, and that's all right. Both will pass. The water keeps moving as you float there. Let your breathing fall into step with the sea. Slow, deep in breath as the water lifts you. Slow, easy out breath as it settles again. Some of it is going to be almost mechanical, like counting numbers in your chest, and all of it is gently pulling you toward rest. The details of antimatter, the graphs and spectra, can drift to the edges now like a faint glow on the horizon. They are still there, but they do not need your attention. For tonight it is enough that some part of you has touched the idea of a universe held together by near symmetries, by tiny merciful imperfections. You can let yourself be supported by that universe, the way your body is supported by the water. Not perfectly still, not perfectly certain, but steady enough, quiet enough. And as you drift, you can trust that the same almost symmetry that spared the cosmos is holding you too through this night. So let me tell you one last thing before we let the story go. A very long time ago, in that first bright instant after the Big Bang, matter and antimatter were not gentle. They met, they collided, they vanished into light, whole oceans of particles and antiparticles, rising and falling in fractions of a second, the way waves rise and fall on a stormy sea. Now think about where you are, not a storm, not an explosion, just a body, your body, resting in a room, a chest that rises and falls more slowly than any early universe wave, a heart that beats quietly, neurons that still hold on to a faint outline of this idea, even if the rest of you is already drifting away. Here's what we do know. The same laws that allowed almost everything to annihilate, that turned nearly all that raw stuff into radiation, also permitted a tiny imbalance, a few extra grains of matter left over when the great accounting was done. So simple, it's almost funny. For every billion pairs that destroyed each other, maybe one lonely proton remained. Those survivors cooled. They joined into atoms. Those atoms fell into clouds, and those clouds into stars, and those stars cooked heavier elements that would one day be bones and blood, and the sodium and potassium that let your neurons whisper to each other in the dark. The numbers that describe antimatter at CERN, The delicate symmetries and almost symmetries are the same numbers that describe how calcium sits in your skeleton, how oxygen binds in your lungs, how a tiny current travels along a nerve and becomes a thought. The world that once blazed with annihilation is the same world that now holds you, very quietly, in place. In a way, your rest tonight is an echo of that ancient process. Energy cooling into structure, chaos settling into pattern. Universe that once shouted in gamma rays, now speaking in the small, slow language of a tired body deciding to stop moving for a while. Questions rise, the way those first particles rose from the vacuum. What is antimatter, really? Why was there that extra bit of matter? We honestly don't know for certain, and some of it is going to stay unknown, at least for you, at least for now, because the part of your mind that chases answers can also learn to be still. Thank you for walking through this, for lending your attention to a story that started long before anyone could listen to it. If you stayed awake the whole way, you carried that story with you. If you fell asleep somewhere back near Dirac, or near the first antihydrogen atoms, that's where the universe quietly took over the work. So now you can let go of antimatter, and of symmetry, and of why there's something instead of nothing. You can trust that the experiments will keep running, that reality will continue its slow unfolding whether you're watching or not. When you're ready, you can return to curiosity and to consciousness. And until that beginning arrives again, you can rest inside the small, improbable fraction of matter that did not burn away, and let the rest of the questions fade into silence.